Hello everyone, myself Harsh Kumar, student of BSc Chemistry on the second year. This is my video for visually impaired on topic aldehydes and ketones. Aldehyde and ketones constitute two isomeric series of compounds, both of which contains the carbonyl group in their molecules and are therefore collectively known as carbonyl compounds. Aldehyde have one hydrogen atom and one alkyl or aryl group linked to the carbonyl group, while ketones have two alkyl or aryl groups attached to the carbonyl group, as shown below. R and R dash may be simple or substituted alkyl or aryl groups. The aldehyde are said to contain the functional group CHO, commonly referred to as aldehyde group, while ketones contain the functional group CO, generally termed as ketonic group when present in ketones. Ketones in which the group R and R dash attached to the ketonic group are the same are termed as simple ketones, and those in which R and R dash represent different groups are known as mixed ketones. The presence of carbonyl group in both aldehyde and ketones is responsible for the close similarity in their methods of preparation and properties. However, due to the presence of free hydrogen in their molecule, aldehydes are more reactive than ketones and also differ from them in certain aspects. Structure of carbonyl group. The carbon-oxygen double bond of carbonyl group is composed of a pi bond and a sigma bond. Moreover, in the molecules of aldehyde and ketone, the carbon atom of carbonyl group is also linked to two other atoms by sigma bond. Thus, the carbonyl carbon is involved in the formation of three sigma bonds and one pi bond. According to the molecular orbital theory, the carbonyl carbon of aldehyde and ketones make use of three sp3 hybrid orbitals in the forming of three sigma bonds. Such bonds lie in the same plane with angles of approximately 120 degrees between them. The pi bond between the carbon and oxygen is formed by the sideways overlapping of the remaining half-filled p orbital of carbon with the similar orbital of oxygen. The above discussion make it clear that a carbonyl carbon oxygen and the two atoms directly attached to the carbonyl carbon lie in one plane. The planar nature of the part of the molecule which immediately surrounds the carbonyl carbon is supported by electron diffraction and spectroscopic studies of aldehyde and ketones. Another important aspect of the structure of carbonyl group arises from the different electronegativities of carbon and oxygen atom. Due to its greater electronegativity, the oxygen atom attacks the electrons of double bond, particularly the pi electrons cloud, strongly towards itself. As a result, the electrons are not equally shared and there is greater electron density around the oxygen than around the carbon atom. In other words, the carbonyl group is a polar group, oxygen having a small negative charge and carbon having a small positive charge. The polar nature of the carbonyl group is probably best indicated by representing it as a resonance hybrid of the following two structures. The last dipole moment 2.3 to 2.8 d of aldehyde and ketone support the polar character of carbonyl group. Comparison of carbonyl group and ethanylic double bond. It may be interesting to note that the carbonyl group is similar to ethanylic double bond as in many respects. Both of them consist of a sigma bond and a pi bond, make use of sp2 hybrid carbon for their formation, are planar in nature, and readily undergo addition reactions. However, the carbonyl group differ from the ethanylic bond in the following respects. First, carbonyl group is apolar in character while ethanylic double bond is not. Second, it is not necessary that a reagent which adds to the carbonyl group must also add to ethylene double bond and vice versa. Third, addition reaction across carbonyl group are initiated by nucleophilic reagent while ethanylic double bond undergoes electrophilic addition reaction. Nomenclature. First, aldehyde. They are named either according to the common or IUPAC system as explained below. First, common system. In this system, aldehyde are named after the acid which they give rise to on oxidation. The suffix -ic acid of the name of the acid is replaced by the word aldehyde. Thus, CH3CHO gives acetic acid on oxidation and is therefore named as acetaldehyde. Similarly, benzaldehyde forms benzoic acid on oxidation and is therefore named as benzaldehyde. This system is mainly used for aromatic and simple aliphatic aldehydes. Second, IUPAC names. These names are given in accordance with the general IUPAC rules. The longest chain carrying CHO group is selected. The corresponding word root and the primary suffix are written. This is followed by attaching the suffix AL in the place of final E. The positions of substituent, if any, are indicated by suitable names, numbers, and aldehydic carbon always getting the number 1 because it is a chain terminating group. For this reason, the number of aldehydic carbon is not usually mentioned. It is taken for granted that it must be the number 1. For aldehyde in which CHO group is attached to a ring, the suffix carbaldehyde is added to the name of the ring. Ketones. The two systems of naming ketones are as follows. First, common name. The common name of ketones are obtained by adding the word ketone to the names of the alkyl or allyl group present in the molecule. These names are mainly used for aromatic and simple aliphatic ketones. For example, CS3CO CS2 CS3 is named as methyl-ethyl ketone. IUPAC names. IUPAC names of ketone carry suffix O and E and are given according to the usual rules. The longest chain containing the carbonyl group is selected from the name of the corresponding hydrocarbon. The suffix E is replaced by 1. The carbon of the ketonic group is assigned the minimum possible number along the straight chain of carbon atoms and substituent group carrying other suitable members. Certain ketones, particularly aromatic ketones, are allowed to retain their common names. For example, acetophenone and benzophenone. Formation of aldehyde and ketones. Formation of aldehyde. Aldehydes are formed during many chemical reactions. Of these, we would consider only those important reactions which are actually used for preparative purposes. First, oxidation of primary alcohol. Aldehydes can be obtained by the oxidation of primary alcohols. However, this method suffers from a serious limitation because the aldehyde formed are further oxidized to carboxylic acid. The oxidation of aldehyde to carboxylic acids generally takes place even with the milder oxidizing agents than those required for the oxidation of primary alcohol to aldehyde. Therefore, it is difficult to stop the oxidation up to aldehyde stage. This problem can be overcome if the aldehyde formed is removed by the reaction mixture by its distillation as soon as it is formed. It is often possible to do so because the aldehyde have lower boiling points than corresponding alcohols and they can be distilled away from the mixture. As shown above, the oxidizing agent usually employed in the reaction is a solution of potassium dichromate in dilute sulfuric acid. However, if the alcohol has poor solubility in water, a solution of chromic anhydride CrO3 in water, acetone, and sulfuric acid is commonly used. This is known as Jones reagent. Special oxidizing agent. The above mentioned of preparing aldehyde involving the distillation of aldehyde from the reaction mixture as soon as it is formed cannot be used in the case of higher aldehydes having high boiling points. Therefore, some special oxidizing agents have been developed for the preparing aldehydes from alcohols. These are first, Sarrett reagent or Collins reagent. It consists of a complex formed by careful addition of CrO3 to excess pyrimidine. A solution of above complex in methylene dichromate CS2Cl2 oxidizes the primary alcohol to aldehyde stage. Second, Corey's reagent. It consists of pyridinium chlorochromate (PCC) formed by mixing chromium trioxide, pyridine, and HCl. It is also used in methylene dichloride solvent to prevent primary alcohol into aldehydes. Third, pyridinium dichromate (PDC). It is obtained by mixing pyridine, potassium dichromate, and HCl in CS2Cl2. Advantages of oxidation of alcohol with above reagents. As it is obvious, the advantage of using any of the above three reagents that they restrict the oxidation of primary alcohol to aldehyde stage. This is because these reagents are used in non-aqueous medium and therefore do not allow the formation of aldehyde hydrates. to take place during oxidation. Since aldehydes themselves are not as easily oxidized further as aldehyde hydrates, the reaction stops at the aldehyde stage. In the case of oxidation by usual oxidizing agents such as acidic potassium dichromate and Jones reagent, the reaction are carried out in aqueous medium where aldehyde formed are converted into aldehyde hydrates, which are readily oxidized to carboxylic acid. Another advantage of using these reagents is that carbon-carbon double bond, if present in the starting alcohol, are not oxidized. Disadvantage of using above reagent. The use of special reagent discussed above for the oxidation of alcohol leads to the formation of chromium-containing waste products which are environmentally very hazardous. At the same time, these reagents are quite expensive and are therefore not frequently used during laboratory oxidation reaction of alcohols. Second, catalytic dehydrogenation of primary alcohols. The oxidation of primary alcohols to yield aldehyde can also be brought about by passing the alcohol vapors over copper heated to 575 Kelvin. The process is generally referred to as dehydrogenation as it involves the direct elimination of hydrogen. The dehydration process does not involve the risk of further oxidation of aldehyde formed. Third, reduction of acid chlorides. Rosamond reaction. The partial reduction of acid chlorides affords another method for the formation of aldehyde. The reaction is usually brought about by the passing hydrogen through a hot solution of acid chloride in xylene in the presence of suitable catalyst. The catalyst employed is palladium, deposited on barium sulfate, and the reaction is stopped as soon as the evolution of HCl gas ceases. This helps to prevent the further reduction of aldehyde formed into alcohol. Next is ozonolysis of alkenes. In this method, the ozonide formed by the reaction between an alkene and ozone is decomposed with a reducing agent to yield aldehydes and ketones. 7. Stephen's reaction. Alkyl cyanide reduction with stannous chloride and hydrochloric acid give rise to aldamine. The aldamine gets hydrolyzed on warming with water to yield an aldehyde. 8. Oxidation of methyl benzenes. Aromatic aldehydes can be prepared by the oxidation of methyl benzenes by different methods and given below. Oxidation of methyl benzene to aldehydes is usually carried out with chromium trioxide in acetic anhydride. The gem diacetate initially formed is isolated and hydrolyzed to get aldehyde. It is also possible to convert methyl benzene into aldehyde by free radical halogenation of methyl benzene followed by hydrolysis of gem dihalide formed. 7. Gattermann-Koch reaction. This reaction constitutes a convenient method for preparing aromatic aldehydes by treating benzene with a mixture of CO and HCl in the presence of Lewis acid and copper chloride. In a similar reaction as Gattermann reaction, HCN is used in the place of CO. 10th, Riemer-Tiemann reaction. This is a convenient method for preparation of phenolic aldehyde, particularly those in which the aldehyde group is present in ortho position to the phenolic group. The reaction is carried out by treating the phenol with chloroform and aqueous sodium hydroxide solution. Formation of ketones. The important methods of preparing ketones are described below. Oxidation of secondary alcohols. Ketones can easily be prepared by the oxidation of secondary alcohols. The oxidation is usually effected by acidic sodium or potassium dichromate, potassium permanganate, or chromium trioxide in a variety of solutions. There is no risk of further oxidation of ketones taking place as ketones are not easily oxidized. Catalytic dehydrogenation of secondary alcohols. Ketones can also be obtained by the dehydrogenation of secondary alcohols by passing their vapors over copper heated to 575 Kelvin. Third, reaction with nitrile Grignard reagent or organolithium compound. Reaction of nitrile with a Grignard reagent or alkyl lithium followed by hydrolysis yield a ketone. These days, another type of organometallic compound known as lithium organocuprate, where R may be any alkyl or aryl halide, are being increasingly used for preparing ketones from acid chlorides because the reaction involved does not suffer from any drawbacks. Fifth, reaction of carboxylic acid with alkyl or aryl lithium. When carboxylic acid is treated with 2 molar equivalent of alkyl or aryl lithium followed by a reaction with water, it leads to the formation of ketones. Ketones can also be obtained by distillation of calcium salt of carboxylic acid other than formic acids. Sixth, from 1,3-diethylines not including in the syllabus. This reaction involves conversion of 1,3-diethynes into the dialkyls derivatives, then the subsequent hydrolysis of the dialkyls derivatives to form ketones. Fiedel-Crafts acylation. This method is specifically used for preparation of ketones in which the ketonic group is attached to at least one aromatic ring. It consists in treating an aromatic compound with an acid halide in the presence of a Lewis acid such as anhydrous aluminum chloride. 8. Hydration of alkynes. Hydration of homologous of acetylenes leads to the formation of methyl ketones. 9. Ozonolysis of alkenes. Ozonolysis of alkenes, in which the double bond is next to a position of branching of the carbon chain, also leads to the formation of ketones. 10. Acetoacetic ester synthesis. Methyl ketones can be conventionally obtained from alkyl derivatives of ethylene acetoacetate, popularly known as acetoacetic esters. The method involves the conversion of acetoacetic esters into acetoacetic ester by treatment with sodium ethoxide. Subsequent treatment with alkyl halide yields alkyl acetoacetic ester. This is subjected to hydrolysis and the beta keto acid thus form obtained is heated to get methyl ketones. Physical properties of aldehydes and ketones. First, physical state. With the exception of formaldehyde, which is a gas at the room temperature, most common aldehydes and ketones are liquid at ordinary temperatures. The lower molecular weight aldehyde have sharp and rather unpleasant smells, but higher molecular weight aldehydes and ketones are pleasant smelling. In fact, some ketones are used in perfumes. Second, boiling points. The boiling points of aldehyde and ketones are lower than those of alcohols and carboxylic acid of approximately equal molecular weights. This is due to the fact that unlike alcohols and acids, there are no effective hydrogen bonds present between aldehyde or ketone molecules. However, due to this highly polar nature, there is appreciable intermolecular attraction in the aldehydes or ketones. As such, their boiling points are higher than those of hydrocarbons and ethers of comparable molecular weight. Melting points. Melting points of aldehyde and ketones do not show any regular trends with the increase in molecular weight, as is clear from the above table. Solubility. Aldehydes and ketones containing up to 5 carbon atoms are more or less soluble in water, but the solubility falls rapidly with the increasing molecular weight. Higher members as well as aromatic aldehydes and ketones are partially soluble. The solubility of lower aldehydes and ketones in water is due to the formation of intermolecular hydrogen bonding involving the carbonyl group as shown ahead. Chemical properties of aldehyde and ketones. Reactivity of carbonyl group towards nucleophilic attack. The carbonyl group contains a double bond between two heteroatoms, that is carbon and oxygen. Since the oxygen is more electronegative than carbon, the bonded electrons, particularly the pi electrons, are pulled strongly towards oxygen. As a result, the carbonyl group is very polar group. The carbonyl group carbon being electron deficient and carbonyl oxygen being electron rich. Moreover, the carbonyl group is flat and can therefore be rapidly attacked from above or below in a direction perpendicular to the plane of the group. It is quite obvious that the reaction of the polarized carbonyl group could be initiated either by the attack of nucleophilic reagent on electron deficient carbon or the attack of electrophilic reagent on the electron rich oxygen. However, out of electron deficient carbon and electron rich oxygen, the former is relatively less stable. Therefore, most of the reactions of aldehyde and ketones involve the attack of nucleophilic reagent on the relatively less stable electron-deficient carbonyl compound carbon and ultimately led to the formation of aldehyde addition product. Mechanism of nucleophilic addition reaction. The nucleophilic addition reaction to the carbonyl compound initiated by the attack of nucleophile on the carbonyl carbon. This leads to the formation of a transition state in which the hybridization of carbon changes from sp2 to sp3. This leads to the decrease in the electrophilic. For nucleophilic attack, it enables oxygen to acquire the pi electrons without having to accommodate a negative charge as shown. It should be noted that, however, if the reaction solution is made too acidic, the H-positive ions would combine with the attacking nucleophile reagent as well. This would suppress the concentration of the attacking nucleophilic species and thus adversely affect the nucleophilic attack. It should be noted that addition of powerful nucleophile does not require any acidic catalysis at all. It is only the weak nucleophiles such as alcohol and ammonia derivative which need the assistance of little acidic catalysis. The relative reactivities of aldehyde and ketones in nucleophilic reactions. First, steric factor. In the transition state of nucleophilic attack on the carbonyl carbon, the carbon starts forming a bond with the attacking species and tends to change from the tetragonal to tetrahedral state. Now, the larger size of the alkyl or aryl group attached to the carbonyl group, the more crowded will be the transition state. As the transition state gets more and more crowded, the steric hindrance of the group increases and the formation of the transition states become more and more difficult. Thus, the formation of transition state would be more difficult in the case of ketones than in the case of aldehydes, since ketones of transition state would be more difficult, containing two alkyl or aryl groups attached to the carbonyl group, while aldehydes have only one hydrogen and one alkyl group or aryl group. As such, ketones would be less reactive than aldehydes. Second, electronic factor. In addition to the steric factor, electronic factors are also responsible for the greater reactivity of aldehyde as explained below. Aliphatic aldehyde and ketones. Alkyl groups have electron-releasing inductive effect and in their presence tends to destabilize the transition state by enhancing the negative charge developing on the oxygen. Acidity of alpha hydrogen. Besides providing a site for nucleophilic addition to aldehyde and ketones, the carbonyl group is also responsible for the acidity of alpha carbon atom. In the presence of a base, the hydrogen attached to the alpha carbon can split off in the form of H-positive ion to form a carbanion. The carbanion thus formed accounts for many reactions of aldehyde and ketones. The ionization of beta or gamma hydrogen of saturated aldehydes or ketones is not possible, as the resulting carbanion would not be resonance stabilized. Nucleophilic addition reactions. The addition compound thus formed may itself result the final product, or it may undergo a subsequent elimination or substitution reaction to furnish a more stable product. Nucleophilic addition reaction leading to the formation of new bonds between carbonyl compound and the atoms of some other elements such as oxygen, nitrogen, or sulfur. Addition of sodium bisulfide. Nearly all aldehydes and many ketones react with a saturated sodium bisulfide solution to form crystalline solids referred to as bisulfide addition compounds. In these compounds, carbonyl carbon get bonded to the sulfur of the attacking reagent. Second, reaction with ammonium derivatives. Aldehyde and ketones undergo nucleophilic addition with certain compounds related to ammonium, such as the addition compound initially formed eliminates a molecule of water to yield compound containing a double bond between carbon and nitrogen. As such, these reactions are also termed as addition, elimination, or condensation reactions. The product from usually crystalline solids having sharp melting points and are used for the identification of aldehyde and ketones. Moreover, as these products can be decomposed by boiling with dilute mineral acid to regenerate the parent carbonyl compound, they can also be used for the purification of aldehyde and ketones. mechanism. All the ammonium derivatives represented by the formula H2NG are basic compounds having a lone pair of electron on nitrogen. They act as weak nucleophilic reagent, and their reaction with carbonyl compound is catalyzed in the presence of acids. The hydrogen ions protonate the carbonyl oxygen, and as a result carbonyl carbon is very readily attacked by the basic nitrogen compound. The adduct thus formed subsequently changes to the final product as shown below. Reaction with phenylhydrazine. Reaction of aldehydes and ketones with phenylhydrazine results in the formation of phenylhydrazones. In the place of phenylhydrazine, substituted phenylhydrazines are also frequently employed. The most commonly used subsequent phenylhydrazine is 2,4-dinitrophenylhydrazine Brady's reagent, which readily reacts with the aldehyde and ketones to form yellow, orange, or red precipitate of 2,4-dinitrophenylhydrazones, commonly known as 2,4-DNP. Reactions with semicarbides. Both aldehyde and ketones react with semicarbides, forming semicarbazones. Ketones generally give complex polymeric product with ammonia. Reaction of aldehyde and ketones with primary and secondary amines to form amines and N-amines is discussed later in chapter. Addition of alcohols. Aldehyde and ketones react with alcohols in the presence of anhydrous acid catalysts such as HCl gas to form ethereal compounds called acetals. Acetals contains new bonds between carbonyl carbon and the oxygen atoms of the alcohols. Formation of acetals. Both aldehyde and ketones react with the ethylene glycol in the presence of para-toluene sulfonic acid PTS to yield respectively cyclic acetals. Use of acetals as protective groups. Unlike aldehyde and ketones, ketals are very stable to bases but are hydrolyzed back to aldehydes and ketones upon treatment with acids. Therefore, their formation is used as a mean of protection a carbonyl group in the certain reactions where it may otherwise interfere with the desired reaction. Protection is the process of preventing a group from taking part in an undesired reactions by converting into a new, less reactive group from which it can be regenerated at a later stage. Nucleophilic addition reaction leading to the formation of carbon-carbon bonds, carbon ion as nucleophilic reagent. We would now take up reaction in which carbon ions constitute the attacking nucleophilic reagent. Most of these reactions are of the great synthetic importance since they lead to the formation of carbon-carbon bond. Addition of hydrogen cyanide. Hydrogen cyanide adds to most all aldehydes and ketones to form alpha-hydroxynitriles, usually known as cyanohydrins. Cyanohydrins are useful synthetic substances because they can be easily converted into other compounds having new functional groups as illustrated below. The alcoholic part of cyanohydrin can undergo acid catalyzed dehydration to form unsaturated nitriles. They are easily hydrolyzed to form carboxylic acids. The nitrile group present in them can be reduced to primary amines by catalytic dehydrogenation. Addition of Grignard reagent. Grignard reagent reacts with aldehyde and ketones to form addition products which are readily decomposed by water, preferably in the presence of an acid such as HCl or H2SO4 to yield alcohols. Addition of salt of terminal alkynes. When treated with terminal alkynes in the presence of sodium and liquid ammonium, addition of sodium salts of alkynes to the carbonyl group takes place. The product formed on acidification gives rise to alcohols which contains carbon-carbon triple bond. Reformat-Sky reaction. This reaction consists in treating aldehyde or ketones with an alpha bromoester and metallic zinc in the presence of diastereobenzene. The addition product initially formed is decomposed in the presence of dilute mineral acid to yield beta hydroxy esters. Aldol condensation. In the presence of dilute base, two molecules of an aldehyde or a ketone having alpha hydrogen atom combines to form beta hydroxyaldehyde or beta hydroxy ketones. The hydroxyaldehyde obtained from acetaldehyde was originally named aldol, and consequently the reaction came to be known as aldol condensation. It may be noted that in every case, the product contains a carbon-carbon bond between the carbonyl carbon of one molecule and the alpha carbon of the second. Aldol condensation can also take place in the presence of acid. However, the acid catalyzed condensation is not so efficient, and addition product initially formed readily undergoes dehydration to alpha beta unsaturated carbonyl compound as final product. Claisen-Smith reaction or Claisen reaction. This reaction is a special case of crossed aldol condensation and may be defined as base catalyzed condensation of an aromatic aldehyde and aliphatic aldehyde or ketone to form alpha beta unsaturated aldehyde or ketone. For example, reaction between acetaldehyde and benzaldehyde in the presence of aqueous alkali metal yields mainly cinnamaldehyde. In the above reaction, initially two products are obtained. One is the self-condensation product of acetaldehyde, while the other is a crossed condensation product with the main product. This product in which beta hydroxy group is activated by phenyl group loses water immediately to form alpha beta unsaturated aldehyde. Benzoin condensation. Aromatic aldehyde which do not contain alpha hydrogen atoms cannot undergo simple aldol condensation. However, in the presence of potassium cyanide, they undergo self-condensation in a different manner to form product known as benzoins. Perkins reaction. Closely related to aldol condensation is the Perkins reaction, which involves the addition of acid anhydride to aromatic aldehyde in the presence of base. The base commonly employed is a sodium salt of carboxylic acid, from which the anhydride is derived, and the addition compound initially formed ultimately yields an alpha beta unsaturated acid. Only aromatic aldehyde are used in Perkins reaction because they do not contain alpha hydrogen. Aldehydes containing alpha hydrogen undergo the more rapid self-condensation in the presence of bases. Conventional reaction. This is another reaction closely related to aldol condensation. It involves the condensation between aldehyde or ketone and a compound having an active methylene group in the presence of a base, which is usually an amine. In general, the reaction may be represented as below. Munch reaction. This is a reaction between aldehyde and amine and an active methylene compound. The aldehyde usually taken is formaldehyde and the amine commonly employed is dimethylamine. The reaction can take place in neutral acidic or alkaline medium, and the product formed is properly known as Munch base. Munch reaction can proceed through different mechanisms depending on the reactants and conditions employed. The above mechanism for the base catalyzed reaction. The fatigue reaction. This is the reaction between aldehyde or ketones and a type of compound known as phosphorus yields to form substituted alkenes. The phosphorus yields generally used are alkadines, triphosphorenes. Halogenation of ionizable aldehydes and ketones. In the presence of suitable acid or base, alpha hydrogen on aldehydes or ketones which contain alpha hydrogen can easily be halogenated at these hydrogens to form alpha aldehydes or ketones. Base promoted halogenation. In the presence of suitable base such as OH negative ion and CH3CO negative ions, one or more alpha hydrogen or of carbonyl compound get replaced by corresponding numbers of halogen atoms. It may be pointed out that aromatic aldehydes and ketones can also undergo electrophilic substitution reaction such as halogenation, nitration, sulfonation involving the aromatic nucleus. It may also be recalled in this connection that carbonyl group is a deactivating and meta-reacting. Reduction. Reduction to alcohol. Aldehydes can be reduced to primary alcohols and ketones to secondary alcohols either by hydrogenation in the presence of catalysts such as nickel, palladium, or platinum, or by reducing agents like lithium aluminum hydride LiAlH4 and sodium borohydride NaBH4. Reduction to methylene group. The carbonyl group in aldehyde and ketones can also be reduced to methylene group to form hydrocarbons. This is generally achieved by two methods. First, Clemmensen reduction. This involves the reaction of aldehyde or ketones with a zinc amalgam and concentrated HCl acid. The reaction works well for ketones but not for aldehydes. Wolff-Kishner reduction. In this method, aldehyde or ketones is heated with hydrogen and a strong base like potassium hydroxide or potassium tert butoxide. Reduction with HI. Aldehyde and ketones can also be reduced to corresponding hydrocarbons by heating with HI in the presence of red phosphorus. Biomolecular reduction. In the presence of magnesium usually employed in the form of amalgam, aldehyde and ketones undergo biomolecular reduction to form symmetrical glycols generally known as pinacols. Oxidation. Oxidation of aldehydes. As stated above, the aldehydes are easily oxidized by the usual oxidizing agents such as KMnO4, K2Cr2O7, H2SO4 or any other oxidizing agent to form corresponding acids. Reducing character. Since aldehydes are very easily oxidized even by mild oxidizing agent, they act as powerful reducing agent. Reduction of tolerance agent. Tolerance agent is a ammoniacal solution of silver nitrate which contains silver in the form of silver ammonium complex. On adding an aldehyde to this agent, the aldehyde is oxidized to carboxylate ion which in ammoniacal solution forms the ammonium salt of the acid. The silver ammonium complex is reduced to metallic silver which gets deposited as a silver mirror on the sides of the tube containing the solution. The reaction is therefore referred to as silver mirror test. Reduction of failing solution and Benedict solution. Failing solution is obtained by mixing equivalent quantity of a solution of copper sulfate and a solution of sodium hydroxide and sodium potassium tartrate. The resulting solution contains a copper tartrate mixture complex which furnishes a small concentration of cupric acid. Benedict solution is comparable to failing solution and is obtained by mixing copper sulfate solution with the solution of sodium carbonates and sodium citrate. Thus, it contains a copper citrate complex which furnishes cupric ions. When halogen is dissolved in the aqueous solution sodium hydroxide, the solution formed contains sodium hydrolytes as shown below. Apart from methyl ketones, haloform reaction is also given by compounds containing such groups that will form the methyl ketone structure CH3CO under the conditions of this reaction. Thus, secondary alcohols of the type CH3CHOH are also respond to this reaction since they are easily oxidized to methyl ketone structure. The acetaldehyde is the only aldehyde and ethylene alcohol is the only primary alcohol that also exhibit this reaction. Baeyer-Villiger oxidation. This reaction involves the conversion of ketones into esters by the reaction with per acids. The formation of ester takes place due to the introduction of an oxygen atoms between the carbonyl carbon and the alpha carbon. Cannizzaro reaction. This is a self-oxidation reaction or disproportionation reaction which is undergone by aldehydes having no alpha hydrogen. It consists in treating such an aldehyde with a concentrated aqueous or alcoholic solution of sodium or potassium hydroxide when an alcohol and a salt of carboxylic acid are produced. Test for aldehyde and ketones and distinction between them. First, test of aldehyde and ketones. Aldehyde and ketones can be distinguished by following tests. First, they form crystalline addition product with sodium bisulfate solution. They form yellow or orange colored derivatives with 2,4-dinitrophenyl hydrazine. Second, distinction between aldehyde and ketones. Aldehyde can be distinguished from ketones by the following test. 1. Aldehydes form a silver mirror on warming with tolerance reagent, but ketones do not. Second, aldehyde gives red precipitate on warming with Helling solution or Benedict solution, but ketones do not. Third, aldehydes give a pink color with Sniff's reagent, but ketones do not. Sniff's reagent is a solution of para-rosanilin hydrochloric acid decolorized by passing SO2 into it. Third, distinguish between methyl ketones and other ketones. Distinction between 2-pentanone and 3-pentanone. When a methyl ketone is treated with sodium hypoiodide, a yellow PPT of iodoform is produced. Other ketones do not give this test. This test is known as iodoform test and is used for distinguishing between methyl ketones and other ketones. Thank you.